Hello. So, during the last lecture, we discussed lattices in 3D. We covered simple cubic lattice, cubic P, cesium-chloride lattice, and body-centered cubic lattice, cubic I. We agreed that a conventional unit cell of a BCC, or a cubic-centered cubic lattice, looks something like this. There is one point shared among all 8 corners. Okay, so there is one lattice point shared among all 8 corners, in addition to one lattice point in the center. So we have two lattice points per unit cell. We can look at the thing from above, as we agreed in this plan view, and then we can see these 4 points over here. They are here. They are at height A. There are also these points over here hidden behind these points over here. They are at height 0. And we see this point over here. We see it in the middle, and it's at height A over 2. Remember, in a plan view, we put what we see and at what height they are. So the unlabeled point, these ones, they are unlabeled. They are at height 0, these points over here, and height A, these points over here. Now, if we put atoms at all lattice points, so at all lattice points, if I put atoms, we notice that we pack the spheres more efficiently. We fill the hole. We fill the hole that appears in the case of the cubic P lattice. And that's why these are more, and this is why there are more elements that have such structure, because it is more stable. It's obvious from the picture, it's obvious from this picture that the coordination number, that is the number of nearest neighbors, for the point in the middle, for example, it's 8. Okay, the coordination number is 8. Obviously, if we take this atom in the middle, we find that it has 4 atoms on top and 4 atoms in the bottom, making a total coordination number of 8. It may not be very obvious that all points in this 3D lattice are equivalent to each other. But if we look at this picture, if we look at the yellow outlined cube, we see that the atom in the center has such environment. Okay, now let's look at one of the corners of the yellow outlined cube. We notice that it's at the center of another cube, which is red outlined over here. So indeed, all atoms are in the center of some cube. So they are all equivalent. Now, it's useful to write down the primitive lattice vectors, the PLVs for this lattice, which we can take them to be 100A, 010A, and half A. What are these vectors? This is here is 100A. Okay, so I go 1 in the direction of A, then I stop. I don't go any further. The other one is 010, that is, first I don't move in this direction, then I move in this direction 1, and then I stop. I don't go upward. And the half, which is half, then I go inward half and then upward half. Okay, now to convince ourselves that these are primitive lattice vectors, we have to show that in order to get to any point in the lattice, I need to take integer sum of these vectors. For example, if I want to reach this point over here, one way to do it is to take this vector here once, twice. Okay, so I take 2 of this 010A, Then I take minus, sorry, I take 2 of this half, half, half A. Then I take minus this one over here, which is 0, 1, 0. So indeed, in order to go to this lattice point, I take an integer sum of these primitive vectors. You can try any other point. You will see that you can get to them by any combination of these primitive vectors. Okay, warning. Do not make the mistake by calling cesium chloride structure. Let me erase this. Okay. Do not make the mistake by saying that cesium chloride structure is a BCC lattice. The rule of a lattice is that every lattice point should look identical. There is a point in the body of the cube. This is true, but it is not identical to other points. Okay, it's not identical to other points. So it is not a BCC lattice. It's a simple cubic lattice with a basis that has 2 inequivalent atoms, cesium at 0, 0, 0, and the chlorine at half, half, half. On the other hand, pure cesium is body-centered cubic lattice, where there is a cesium atom at all the points, even in the one in the center. We can also call it simple cubic with a basis, where the basis is cesium at 0, 0, 0, or cesium at half, half, half. So we can call it by 2 names. Either we say cesium is BCC, and in this case, we don't say there is a basis or anything. We just say cesium is BCC. This means it's a cubic lattice where there is cesium in all the 8 corners and 1 cesium in the middle. Okay, so this is one way to say it. It's a BCC lattice. Or we say it's a simply cubic lattice with bases. That is, it's a simply cubic. There are cesium in all 8 corners with a basis. What is the basis? Cesium at 0, 0, 0 and cesium at half, half, half. Okay, these are 2 equivalent ways to say, to name the BCC structure. Now, you might wonder why we are taking a conventional unit cell that has 2 lattice points rather than taking a primitive unit cell with only 1 lattice point. Wouldn't that be easier? The reason we are not taking a primitive unit cell because primitive unit cells are kind of ugly looking. Look here, this is the Wagner-Seitz unit cell for the BCC lattice. It is a truncated octahedron. It has around 18 sites. The lattice point is in the center, so it's an ugly shaped object that is difficult to be dealt with. But if we take this object and stack them one next to each other, they would tile all space, filling all space. Oh, now there is one more type of lattice that we need to discuss, which is the face-centered cubic lattice, FCC, or cubic F. We start with the simple cubic lattice that is 8 corners, that has 8 lattice points at all 8 corners, okay? And then on each face, there are 6 faces of the cube. I insert 1 lattice point in the middle. So the conventional unit cell looks something like this. How many lattice points are there in the unit cell? How many lattice points are there in this unit cell? We observe that first we have 8, right? We have, we have 8 corners. Each one of them has 1/8 of the lattice point, and there are 6 sides, but not all the atoms, not all the lattice points on the 6 sides are inside the conventional unit cell. Only half of it. Only half of it. and this will give me 1 plus 3, which is equal to 4. So the number of atoms in the unit cell is 4. Now, if I look from the top, that is, if I look at this plan view, I see, first of all, the 4 corners. Okay, the 4 corners, they are here. The 4 corners are here. Okay, they are at height A. Underneath them, we have these points over here. They are at height 0. So unlabeled points are at height 0 and A. Then what do we have? We have these points over here. Let's change the color. We have these points over here. They are at height 8A over 2, right? So in the middle of each side, I see these points at height A over 2. And then finally, there are these 2 points, one of them at height 0, one of them at height A, and they are exactly in the middle of the square. Okay, they are at heights 0 and A. So this is how our FCC lattice looks from above. Now, if we fill the lattice points with atoms, our unit cell looks like this. And this is proven to be the most efficient sphere packing. And this is why there are lots of elements that have FCC configuration: copper, silver, gold, calcium. Okay, now something which is tricky to visualize is the coordination number in case of the FCC lattice. It's not so easy to see from here, but one way to see it is to look at one atom on the side. We will see that it is attached to 4 atoms. It's near 4 atoms from this side, 4 atoms on the same plane, and then 4 atoms on the other side. I found this resource over here. If you just copy paste it, if you just copy paste this link to YouTube or to Google, you will see it clearly how the coordination number is 12. In this video also, they show the coordination number of BCC and the coordination number of simple cubic. So I hope by seeing the video, it becomes clearer to you that the coordination number in case of face-centered cubic is indeed 12. Now, let's look at our primitive lattice vectors. Okay. This is a very good primitive lattice vector combination. This is half, half, 0. What is half, half, 0? I go half, then half, and then I stop. So this is this one. And then half, 0, half, which is half. Then I don't move it inward, but then I go upward. So this one over here is half, 0, half. And then there is 0, half, and then half. Okay, so this one is 0, half, and half. Again, to convince ourselves that this is a proper list of primitive units, primitive vectors. Let's see how can we reach this point, for example, over here. To reach this point over here, one way to do it is to go this way. Okay. Then to go this way. So then we take, so first of all, we take this one, which is half, 0, half. Then we take the 0, half, half. Okay, this one is parallel to this. So then we take the 0, half, half. And then we want to take 0, half, half, which is this one. So this one is similar to this one. So indeed, it's an integer combination of these three vectors. We can reach any other point in space using these primitive vectors, and this is why these are very good primitive vectors in case of the FCC. Again, as with the BCC lattice, why we are talking about a conventional unit cell that has 4 atoms and that has 4 lattice points, and not looking at a primitive unit cell that has only 1 lattice point. It's again because, for example, here the Wagner cites unit cell. It is very, very, very ugly, and it's very, very difficult to deal with. So look at this compared to this one. Here I can see atoms. I can see how they are changing, what is the location, how to reach them. But in this one, it is very ugly to deal with. Okay. Also, as in the case of a BCC, I can think of the FCC lattice. So one way to describe the FCC lattice is just saying it's an FCC lattice. This means automatically that it is that it's a cubic lattice with 8 corners occupied, and there are all the faces. There is 1 lattice point in the center of them. But another way to describe the FCC lattice by saying it's a simple cubic lattice with a basis. Where is the basis? I have 1 point at 0, 0, 0 over here, 1 point at half 0 over here, 1 at half 0, half over here, and 1 at 0, half over here. Okay, all other points are equivalent to these points. Okay. Now let's move to a new structure, the sodium chloride structure. This is an example of what we can put together when we have a lattice and a basis. So this is a sodium chloride structure, a very typical salt structure. Sodium chloride is very ionic. Sodium gives up the electrons. Chlorine takes the electrons. And if we look at it carefully, we can see that sodium is forming an FCC lattice labeled cubic F. Okay, so here, if we take sodium to be blue, if we look only at the blue atoms, so if we try to ignore the green ones, we see that sodium by itself has an FCC structure. Also, chlorine by itself has an FCC structure. Okay, so in addition to the sodium atoms that form an FCC structure lattice, there are chlorine atoms as well, and we can describe the position of the chlorine atoms by saying for every sodium atom, there is a chlorine atom displaced by half from the sodium atom. That will get you to all of the chlorine atoms. Here is a plan view. The blue atoms are sodium, the green ones are chlorine. For example, if I start in the right here from the origin, and I go, if I start from the origin and I go halfway here, then halfway inward, then halfway upward, I reach a chlorine atom. So this is why we're saying the chlorine atoms are displaced half from any sodium atom. Okay. When you describe a basis, you should always describe the basis of the primitive unit cell. So here, I don't talk about the conventional unit cell, which has 4 sodium and 4 chlorines. I just say the lattice is a cubic F with a basis, sodium at 0, 0, chlorine at half. I don't say here I have a cubic F with sodium at 0, 0, 0, sodium at half 0, sodium at 0, half, sodium at half 0, half, and then a chlorine at another 4 positions. No, I just say it's a cubic F, okay, where the basis, this is the basis. This is the basis, okay? There is sodium at 0, 0, 0, and there is chlorine at half, half, half. Yeah, if you want to look at the basis, this is the basis, sorry. This is the basis. This chlorine, it's difficult to, so there is this chlorine with, sorry, this sodium with this chlorine. So this is the basis, okay? Okay, so all we need is the position of one sodium and one chlorine. By the way, the choice of chlorine half, half, half is not fixed. I can also choose this chlorine over here, no problem. So I can take my basis to be this one over here also. So it doesn't have to be only 0, 0, 0 and half, half, half. It can be 0, 0, 0 and 0, half, 0. Or half 0, 0 if I want to take, this basis over here, okay, this sodium and this chlorine. So there are several ways to describe the basis. It's not only half, half, half. We can take it to be 0, half, half, or half 0, 0, or whatever, whichever chlorine atom close to this sodium atom. Okay, so there are various ways to describe the same lattice. Fine. One last structure we are interested in. Remember that we agreed we will only be dealing with structures, 3D structures where the axes are perpendicular. Okay, we will not be looking at, because there is another very interesting structure which is also heavily packed, like the FCC. That's the HCP, the hexagonal, the HCP. Just check it out. The hexagonal close packed structure, or HCP, it's also heavily packed, okay? But we are not discussing it in this course because the axes are not perpendicular, but feel free to study it on your own. Okay, there are many elements out there that have sodium chloride like structures. Here are some examples: potassium chloride, lead sulfide, sodium silver bromide, etc. Now, the last structure we will be looking at is what is called diamond structure, C. Also, silicon and germanium have the same structure, so some people call it silicon structure or germanium structure. If we look at it, it seems like we have, it's a cubic one, okay, where there are lattice points in all 8 corners. There are also lattice points in the middle of all the bases. So this looks like an FCC indeed. But if we just say it's a cubic F or FCC structure, it's not enough, because there are some atoms like this one over here, for example. It is not described like this one over here. It's not in the FCC. It is not one of the corners, and it's not one in the middle of the faces. So I need to find another way to describe this lattice. If we look at the plan view, we see that indeed we have that of the FCC. So we have these 4 in the corners. We have this one in the middle, which corresponds to this one over here and this one over here. We have these ones in the middle of the faces that correspond to the middle of the faces. Okay, But there are also these extra atoms that are at heights 1/4, 3/4, 1/4, and 3/4. So they are in the middle of the cube and somewhere in the middle of the cube, and they are at heights 1/4, 3/4, 1/4, 3/4. This is a cubic F. It's a cubic F, but with a basis where we have carbon at 0, 0, 0, and there is carbon at 1/4, 1/4, 1/4. Okay. Let's look at the structure. Gallium arsenide. Is it a lattice? Right? Is it a lattice? So what we see, let's look at the yellow stuff. The yellow stuff, they are occupying all 8 corners and they are occupying all the faces, right? So there are the yellow stuff have FCC, and then there is this blue thing displaced from the yellow thing by quarter, quarter, quarter. So this indeed is a carbon-like structure with yellow at 0, 0, 0 and blue at quarter, quarter, quarter. Okay, let's now move to something else. You remember when we talked about lattice, we said that the position of a lattice point is given by the vector r, and it's equal to n1a1 plus n2a2 plus n3a3. So for example, if we want to reach this point over here, T, okay, this point over here, T, we have to go first across along A1, then one along A2, and then one step along A3, okay? And this takes me from O to T. So these 3 coordinates, N1, N2, and N3, we call them, these should be integers, okay? Now, the line joining a lattice point with O is called a crystal direction. So this OT over here is called a crystal direction, and it has this thing over here, HKL, where HKL are N1, N2, and N3. Okay, so this is N1, N2, and N3. Okay, this is the HKL. So this crystal direction over here is 1, 1, 1, because we want 1 along the x-axis. So think of A1, A2, and A3 like the I vector along the x-axis, J vector along the y-axis, and K vector along the z-axis. Okay, so in order to reach point T, I go 1 step along the I vector, 1 step along the J vector, and 1 step along the K vector. And this over here in purple, OT, is called a crystal direction, and I denote it by HKL, which is N1, N2, N3. That is 1, 1, 1 in this case. So this is about a crystal direction. It's our new definitions. Okay. We use the coordinates N1, N2, and 3. We choose the set of the smallest integers. That is, if I can reach T by going 10, 10, 10, or by 1, 1, 1, I choose the 1, 1, 1. Okay. So we choose the set of smallest integers, multiply by the lowest common denominators, or simplify by the common factor if necessary. So for example, this direction here, this is crystal direction OM, okay, I have to get the coordinates of OM. So how do we reach this point M? Okay, how do we reach it? We go 1 step along the x-axis, right? And then half step along the y-axis, and then we stop. So it is 1, half, 0. But N1, N2, and N3 should be integers. So I should turn this into integers, and this happens by multiplying by 2. So this direction over here, OM, is 2, 1, 0. Okay. Now, if we have negative directions, we write it with a top bar. So for example, if this is my O and this is my N, and ON is my crystal direction, okay? How do we go from O to N? We go like this. We go -1 along the x-axis, right? This is the x-axis over here. This is parallel to the x-axis. Then I go -1 along the y-axis, and then I stop. All right, so this is the y-axis in this direction, but I go one step in the opposite direction. So I am at -1, -1, 0. But when we write the crystal direction, we don't say -1, -1, 0. We say 1 bar, 1 bar, 0. Okay, so it's very easy to determine the crystal direction. I determine the coordinates of the point I'm interested in, and then I turn it into HKL, okay? The numbers should be integers, and if there is negative, it should turn into a bar. Okay, so this is crystal direction. So we discussed crystal planes and crystal, we discussed crystal directions, right? Yes. Now, crystal planes. It's important to have a notation system for atomic planes, since these planes influence the properties of the crystal. Optical properties, reactivity, surface tension, etc. Within a crystal lattice, it's possible to identify sets of equally spaced parallel planes. These are called lattice planes. So if we look, for example, at this crystal, we can see these planes, they are parallel to each other. If I look at this crystal, we can see that these planes are parallel to each other. These planes are parallel to each other. These planes are parallel to each other. So these, we call them crystal planes, okay? Miller indices, this is how we describe crystal planes. So Miller indices, HKL, are a symbolic representation for the orientation of atomic plane in a crystal lattice. So there are crystal planes, but how do we describe them? We describe them using Miller indices. Notice there is also HKL, but these are round brackets rather than square brackets. Okay, so how do we determine the HKL? First, okay, I'm gonna show you examples so you will see it's not super difficult, but first, these are the four, this is how we do it. So we determine the intercepts of the plane along each of the 3 directions, okay? So wherever it hits the X, Y, and Z axis, then I take its reciprocal. So if it hits the X-axis at half, it means it's 2. I take the reciprocal. And finally, if we have fractions, we multiply by the lowest common denominator so as we get rid of the fractions. Let's look at examples immediately. Okay, so this is one example. And look here at the plane that I'm interested in, okay? So if we look at this plane, we see that it hits the x-axis at this point over here. It is labeled 1, 0, 0. It does not hit the y-axis. It's parallel to the y-axis. It does not hit the z-axis. It is parallel to the z-axis. So what are the intercept points? It hits the x-axis at point 1, right? It doesn't hit the y-axis and it's parallel to it. So we say it's infinity. Okay, if it's parallel to an axis and it doesn't hit it, we say it's infinity. Similarly with the z-axis. Now we take the reciprocals. 1 over 1 is 1. 1 over infinity is 0. 1 over infinity is 0. And this is the smallest ratio, 1, 0, 0. So the Miller indices for this plane over here is 1, 0, 0. Let's take another one. Let's take another one. So this point here is 1, 0, 0, and this point here is 0, 1, 0, okay? And it doesn't hit the z-axis, it's parallel to it. So it hits the x-axis at point 1. Okay, it hits the y-axis at point 1, y equal 1. It does not hit the z-axis, so it's infinity. And now I take the reciprocals, 1 over 1, 1 over 1, 1 over infinity. And the smallest ratio is 1, 1, 0. So the Miller indices of this crystal plane is 1, 1, 0. Let's take another example. So similarly, this plane, it hits the x-axis at 1, the y-axis at 1, the z-axis at 1. So if I take the reciprocals, I get the Miller indices for the plane 1, 1, 1. Okay. This one over here, it hits the x-axis at half 0, 0. It hits the y-axis at 0, at 0.010. It doesn't hit the z-axis. So it hits the x-axis at half, the y-axis at 1, the z-axis at infinity. And then I take the reciprocal, so I get 2, 1, 0. Okay, one last example. This plane over here, it hits the x-axis at -1. It doesn't hit the y-axis, so infinity. It doesn't hit the z-axis, so infinity. Then I take the reciprocal, so it is -1, 0, 0. But I don't put -1, I put 1 bar, 0, 0. Okay, now, if I take, for example, this case, where I look at the crystal direction and the crystal plane at the same time. So in a blue, we see the crystal direction. It is 2, 3, 3. So if we look at this plane in yellow, this is the crystal plane. So the crystal plane is in yellow. Okay. So if I want to calculate the Miller indices, it hits the x-axis at 3, right? It hits the y-axis at 2, and it hits the z-axis at 2. And then I take the reciprocals. Then I look at the reciprocals. 1 over 3, 1 over 2, and 1 over 2. Okay. If I multiply by 2, I get 2 over 3, 1, and 1. But I need to get rid of this 3, so I multiply now by 3. So I get 2, 3, 3. And this is these are my Miller indices. These are my Miller indices for this plane over here. Now, if I want to reach this point over here, it's not very easy to see. Okay, if I want to reach this point over here, I go the crystal plane for the crystal direction is also 2, 3, 3. Okay, it's also, we are also assuming that the crystal direction here is 2, 3, 3. Now, what I'm saying here is for a cubic system, the crystal direction HKL and is always perpendicular to the crystal plane HKL. So if I take a crystal direction with direction, for example, 1, 2, 1, this will be perpendicular to the crystal plane with Miller indices 1, 2, 1. Okay. Or if I take the crystal direction 0, 1, 1, this will be perpendicular to the crystal plane with Miller indices 0, 1, 1. Okay, so this one you have to know. That the crystal direction with indices HKL is perpendicular to the crystal plane with indices HKL. Okay. As we have here. Yeah. Again, so this one is 100. This one is 100, 1 bar 00. This is 110. This is 111. This is 002. This is 1 bar 00 because it's in the opposite direction of the x-axis, so it's minus 100. Now 100, 1 bar 00, 200, 300, they are all parallel to each other. 111, 222, 333 are all parallel to each other. 002, 001, 003, 004 are all parallel to each other. We note that HKL with round bracket, they denote a plane, Miller indices, and HKL with a square bracket, they denote a crystal direction, okay? Now, extra exercises. So here what I'm giving you, tetragonal unit cells shown below. Sketch the correct planes or directions as shown by the appropriate Miller indices in each case. So for example, in the first one, this is Miller indices, right? So this is Miller indices. 1, 2, 4, because it has round brackets. So I need to sketch the plane. Okay, so here we have to remember that to get the Miller indices, we take the intercepts and we flip them. So if I get 1, 2, 4, it means I had 1/2 intercept with the x-axis, 1 over 1 at it intercepts the x-axis at 0.1, it intercepts the y-axis at half, and it intercepts the z-axis at 1/4. So now if I come to my drawing, to my figure, so it intercepts the x-axis at this 0.1, it intercepts the y-axis here in the middle, and it intercepts the z-axis somewhere here. It should be at 1/4. Okay, and now this is the plane. Okay, but it must be okay, so I do the same thing here in case of 010. Here is 1 bar 0. This is not Miller indices. This is the crystal direction. Okay, this is the crystal direction. So it's 1 bar 0. So how do we go to 1 bar 0? I go along the x-axis 1, then 1 bar, which is opposite to the y-axis here, this axis over here, I go, and then I stop. So this is the direction I'm talking about. Okay, and another way to see this thing is this thing. Okay, so I leave you to continue this exercise on your own, and hopefully we go through them during live session on Tuesday. The very last thing, by the way, in this exercise here, I'm giving you the planes and the directions, but you need to find the Miller indices and the directions. Okay, so it's the opposite of the first exercise. The very last thing is the distance between successive planes. That is, if I give you 2 successive planes, like what we saw here. So these 2 are called successive planes, which means they come right next to each other. These 2 are successive planes. These 2 are not successive planes. This one and this one are not successive planes because there is one plane in the middle. So the distance between two successive planes in a set HKL is determined by the Miller indices. This is the formula if the three crystallographic directions are orthogonal, okay? So if they are successive, it means this n is 1. In case of the simple cubic, when A equal B equal to C, we get this distance to be A over square root H square plus K square plus L square. Also, I want you to work on this to solve it on your own, to derive it on your own. Okay, so you need to do the research on your own and to make sure that you get this distance to be A over square root H square plus K square plus L square. So that's it for today, and tomorrow, and we will have one more recorded session this week. Bye-bye.